you may wonder, why am I giving this talk? So let me give a few introductory remarks. About a year ago, I was invited to give a banquet lecture at a conference in Penn State University this June. And the first thought that came to my mind is, boy, am I getting old. People ask me to give these banquet talks. And so the second thing I did was think about what I'll discuss. They asked me to speak about future frontiers in astrophysics. And I thought about giving some advice and roadmaps, guidelines for young people in terms of choosing research topics for the next decade or two. And so young people were my target audience, and I tried to think about what the best advice would be for them based on my own experience. So then I gave my talk at the conference, and I noticed, to my surprise, that there was a lot of excitement among the young people to the talk that I gave. People were standing by the elevator afterwards, speaking for another hour or two about the subject. And the following day at the conference, I had to leave on a plane, but I heard from the organizers that people mentioned this talk in their talks. And there was a lot of discussion about what I said. And so on the way back on the plane, I thought maybe I should write it up for the benefit of people that were not in the audience. And so, but then I debated that question, because any write-up will not include any equations or quantitative estimates the way I'm used to in the context of the more than 300 papers that I posted in the archive before. And so that would be an unusual write-up to put together. And I was not sure that it's appropriate for me to post it on AstroPH. But then an announcement came about the decadal survey, that it's about to appear within a week, the report. And I realized that unless I put it out within that week, people will think that I wrote my write-up as a reaction to the decadal report, because I talk about future frontiers. And so I decided to write it up. That was 10 a.m. that morning. By 10:30, I then remembered that I have a dentist appointment at 11:30. So I went to my wife and said, I have the muse to write up this thing, and I really should finish it up. But I have this dentist appointment, should I cancel it? And she said, knowing you, I know that the muse will come back. A dentist appointment is much more difficult to arrange, so you should definitely go to the dentist appointment. So I went, and then she was right, and I did have the muse subsequently and finished up the write-up by the evening. And so I posted it on the archive. And the papers usually come out at 8 p.m. the following day. So the preprint came out at 8 p.m. By 8:30, I got emails from Europe, from various places, just to show you that people read it exactly at 8 p.m. and they finished reading it and wrote comments.
8 p.m. Eastern time?
Eastern time, our time.
And you got answers in Europe right
From
away?
Europe at 8:30, yeah. So someone must have been awake. It was from the Netherlands. And following that, I got 100 emails or so. Until even today, I got a few emails about this. So there was a resonant nature to the reaction to my both talk and write-up. And I was wondering to myself, why is that? Why do I get so much feedback from the community? And my answer, actually the answer was provided in the emails that I received. Some of which came from young people, and they said, basically, thank you for bringing this topic up for a discussion. And I realized that this must be the elephant in the room, that everyone is aware of, everyone is thinking about it, but nobody talks about it. So let's discuss the elephant. And you can read, those that have not read the written summary, it's on the archive right here. And actually, Nature magazine asked me for a shortened version, and they will print it within a couple of months. So I'll start by discussing future frontiers in astrophysics, because that was the title that was given to me at the banquet. And I have to start with a disclaimer that comes from the Talmud. Following the destruction of the temple, prophecy became the trademark of fools and babies. And since I'm not a baby, I do not want to sound like a fool. I will not make any prophecies here, but just give you sort of general guidelines as to what are possible frontiers in the future. So let me start with a very distant future, the long-term future, centuries from now. I think that would be one of the most fascinating topics in astrophysics, biology away from the Earth. And what do I mean by that? I mean life in the solar system. People are talking about liquid water in Enceladus, fish in Europa, and so forth. Of course, habitable extrasolar planets will be explored. And perhaps there are civilizations out there. I'm not necessarily pessimistic. I have a flat prior as to what we might expect elsewhere. We should just search the sky and see if there are civilizations similar to ours. And if there are, we might, for example, search for lines associated with fluorescent light bulbs that they have in their cities and find evidence for them. And of course, if there are intelligent civilizations, we might eavesdrop on their radio signals. Now, you might think that this is a very distant frontier, but in fact, people are building now a low-frequency array. This is the one in Australia, the Murchison Whitefield array. There is another one, LOFAR, built in Europe, that will have, at the end of order, 8,000 dipole antenna working between 80 and 300 megahertz. The purpose of that would be to image the hydrogen in the universe at the 21 centimeter line. But since it's redshifted by about a factor of 10 from the epoch of reionization, we're talking about detectors of meter-long wavelengths. And if you look at your FM dial on your radio, you will see that these are the frequencies that we are transmitting information in. And so you can immediately figure out how bright the foreground would be near a big city like Sydney. And these are all radio stations or TV stations in the frequency range that the MWA, for example, is looking at. As you go away towards the desert, the Australian desert, you see less emission, and eventually this experiment will be done in a place that has very, very little interference. But that led me to think together with Matthias Zaldriaga about the possibility of using these instruments to put limits on extraterrestrials, because you could, in principle, eavesdrop on them, and we don't know what we will find. So you can ask a simple question. Suppose there is a civilization just like ours, a twin civilization. How far away will we see it by eavesdropping on its signals if we were to assume that it has the same transmission as we have? And the answer is at a distance of tens of parsecs. These are different integration times for MWA or other experiments. You can see an Earth-like civilization going through the Second World War, for example. That was the brightest period because people were using anti-ballistic missile radars at that time, or shortly afterwards. And so we would be able to see such a civilization out to tens of parsecs. And we have been transmitting for about 50 years as well. So if there is an exact copy to our civilization, tens of parsecs away, we will be able to see it in the relatively near future. And of course, if we see it, we could ask these extraterrestrials questions that we don't have answers to. But that, of course, will feel like cheating in an exam, right? So that's the secular version of cheating in an exam. And the religious version is when you have a supervisor looking over your shoulder. There are other long-term challenges that we can, in principle, approach in laboratory experiments. For example, we can conceive methods of producing the inflaton depending on at which energy the scalar field that was responsible for inflation took place. If the energy scale is the Gutt scale, it might be very difficult for us to produce it in the laboratory, but if it's lower energy, we could, in principle, go after it. We don't know the nature of this scalar field. We can also think about ways of perturbing the vacuum energy density, the cosmological so-called constant in the laboratory centuries from now. In the intermediate term, decades from now, what kind of challenges may we have? In laboratory experiments, of course, we would like to produce or directly detect the dark matter. We would like to detect light from extrasolar Earth-like planets. And by that, I mean actually getting perhaps an image of an Earth-like planet. And you all know about the Terrestrial Planet Finder and Darwin, which are at this point frozen budget-wise. But one of the most exciting frontiers that I think will be realized, there is no way to shy out of this challenge. I think it's a very exciting frontier, and I would highly recommend for young people to consider working in it. And that's gravitational wave astrophysics. And the reason I say that is because it's a new window into the universe. And whenever we open the new window into the universe, we discovered new things that we haven't anticipated. We're all expecting signals from black hole binaries, but maybe there is something else out there that is producing gravitational waves. LIGO will detect the gravitational wave counterparts of short duration gamma ray bursts from compact object binaries. And LISA will map the growth history of supermassive black holes all the way to very high redshifts. It would also, both of these experiments will be able to test general relativity in the regime that it was never tested in, the strong field limit. We are talking about a century after Einstein came up with this theory. It's about time that we find a deviation. There are people that dedicated their full career to finding small deviations in the Newtonian regime. And Erwin knows that frontier very well. And they haven't detected any. That's quite remarkable. In quantum mechanics, there was a lot of advance over the past 80 years. In general relativity, not much. And on the theoretical side, now we are able to actually calculate the space-time around a binary black hole system, and in particular predict the gravitational wave signal that will come out of it depending on the spin orientation and the mass ratio of the binary. In terms of immediate observational frontiers, those that will definitely be very likely to be realized in the near future, there is another one that relates to black holes. This is from a Scientific American article that we wrote with Avery Broderick, and that's getting an image of a black hole. And when we have such an image, I'm sure it will appear on the cover of any textbook on general relativity. So it's of fundamental importance to actually image a black hole. The reason it was not done before is because you need a very high resolution of the order of tens of microarcseconds to actually be able to resolve the nearest supermassive black hole that is the biggest on the sky, which is Sagittarius A star. But we have the technology to do that. And doing that, and we are, in fact, we have, this was actually done already. So I gave a talk about this subject at Caltech 2 years ago, and someone in the audience, a very respected astronomer, came to me afterwards and put his hand around me and said, Avi, you have to realize that there are lots of observational obstacles to doing this measurement. I said, well, thank you very much. I really appreciate it. I didn't tell that person that it was already done. So be careful of advice that you hear from people that worked in an area for a while, because things that cannot be done are done eventually. And in particular, the method for achieving this very high resolution is to use stations, many different stations in constructing a very large baseline interferometer, just like the ones that were constructed at centimeter or tens of centimeter wavelengths, except that you're doing it at millimeter wavelength. And as you all know, the resolution of any telescope is related to its wavelength divided by its diameter. In this case, it's roughly the diameter of the Earth. And if you take a wavelength of 1 millimeter, you end up with a resolution just enough to image, to resolve Sagittarius A star, as well as M87, which has roughly the same size on the sky. And in fact, we are just putting the finishing touches on a paper that should come out very soon within the coming weeks, in which we put constraints on the spin of the black hole at the center of our galaxy based on existing data.